the right movers are filled up to P equal to Kf and they are empty afterwards. So the energy of right movers is Vf into P minus Kf. So that means energy is positive and therefore empty when P is greater than Kf. Energy is negative when P is less than Kf and therefore it is filled up. So with left movers it's P plus Kf into Vf with a minus sign. So So this is the definition of the Virasoro primary state, and so it has this property. So you cannot create when it's something is already there, and you cannot destroy when nothing is there. So you have these two conditions, and then of course this B is the combination, or it's just the product of things which annihilate when something is not there and tries to create when something is already there. So the action of B on the Virasoro primary state is zero. So the momentum of the fermion normal order is defined like this. We have to calculate the eigenvalue of the momentum. So I've told you that why is it defined in this peculiar way, because the difference between this and the what you would normally refer to as momentum, which is C dagger C into P summed over all P. So after all, what is C dagger PCP is the number of fermions with momentum P. So that multiplied by the momentum summed over all momentum is the total momentum of the system of right movers. So so that definition and this peculiar definition, they differ by an infinite constant. So that means the difference between this peculiar definition and the what you would normally associate as with momentum, that difference is just a constant. So, but it is defined in this peculiar way because if you don't do it this way, the usual way of defining momentum will give you an infinite answer when you act it on the Virasoro primary state. But when you act this particular definition, so this particular definition is acceptable because it only differs from the naive definition, which is intuitively obvious by a constant, which happens to be an infinite constant. It's still a constant. So now the point is that when you act this normal order momentum on the Virasoro primary state, so the question is, what is the eigen value of this normal ordered momentum acting on the Virasoro primary state? And in order to calculate that, uh, you have to use these identities, which tells you that if P is less than Kf, the states are occupied and empty otherwise. And then with respect to minus P, that if you first create and then annihilate, you cannot create unless uh, minus P is empty. So minus P is going to be empty when minus P is greater than Kf. So that way, so when you do all that and you act it on the Virasoro primary state, so what you get is basically um, this result. So this acting on the Virasoro primary state together with these identities gives you this result. So all you have to do is evaluate this, and then of course you can do it, count it properly, and you get this result. Okay. So I think this is what I had done, and so I had asked you to do these homeworks. That is, show that the number of the bosons commute with the um, total number of right movers. Okay, the right mover bosons, the right and left will always commute unless they are fermions, which in which case they will anti-commute. But right and left always commute. Uh, so so we had proved that. So I had just given you one sample proof of how to show that B dagger commutes with total number of fermions. Total number of right movers. So similarly, you have to show that the Hamiltonian. See, we remember that the Hamiltonian is just the Fermi velocity into momentum. So you just have to show one of them. That the total number of uh, right movers commutes with the total momentum of fermions. So the question is, mm, what are these commutators? So that's interesting because you see, we are going to so this is the central idea behind this bosonization, where you try to express the momentum, the normal order momentum in terms of the bosons. So the way you do this is you evaluate these two commutators. Okay, so when you evaluate them, you get this result. So you get these two results. Am I going too fast? I mean, all the steps are here, but I'm going a little fast because I'm not sure if I mentioned all these things earlier. I get a feeling that I mentioned some of this earlier. That's one reason why I'm going a bit fast. But stop me if you feel I haven't mentioned any of these things in my earlier talk. Have I or have I not? Have I mentioned these issues earlier? So the whole idea was to write this normal ordered momentum in terms of the bosons. Yes. Yeah. You want to say something? Okay. So when you do this calculation, you will get this. So you will be able to show that the normal ordered momentum commutator with B dagger is again B dagger times this parameter Q with a minus sign. Similarly, the commutator of PR with B is Q with times the B. So this immediately suggests that you should be able to write P of R, as a product of the B dagger and B, because you see, if you take the commutator of this with respect to B, you'll get Q into B again as you're supposed to, namely this. So so you can always think of normal ordered P as summation Q B dagger B plus something else, something which commutes with P, normal ordered P. So this is perfectly reasonable insofar as you believe that uh, this P is fully expressible in terms of bosons and objects that commute with the bosons. So we know that PR acting on the ground state on the Virasoro primary state is pi nr squared by L. So it's intuitively reasonable to add this particular operator to this and claim that these two are mathematically the same things. But that's a very, very serious and non-trivial claim. See, remember that all we have done is that we have shown that this PR commuting with the bosons, this particular form of PR in terms of the bosons has these commutation rules, and also this form also ensures that normal ordered PR commutes with a number of right movers. So it does three things. So it has three things going in its favor. First is it obeys this. The second is it obeys this. Okay, and the third thing is it obeys this one. P commuting with NR will be 0 because bosons commute with NR and NR commutes with NR. So P commuting with PR commuting with NR is 0. But still, these two, so the claim is that these two should be the same. Okay. Now, but that's not going to be, to me, it's not convincing unless I show that how do you show two operators are the same? Whatever happens to this should happen to this. I mean, no matter what you try to do with this, the same thing should be doable with this. So one of the things that you should try is that sure it commutes correctly with the bosons and with NR, but what about with just the single, say, annihilation operator? Suppose I take the commutator of uh, calling this the interaction energy, potential energy. Similarly, with between left and left movers, it would be this. But then you can also have a different sort of interaction because remember that right and left movers are different species. They're kind of completely different objects. So they can mutually interact differently and uh, and you know like the right and right can interact in a certain way and right and left can interact in a different way, so which is why I have put a w there instead of a v. So this v would correspond to the the same species interaction, and w would correspond to the the opposite species interaction. So, but so now, how do you define? So remember that this is a little bit unfamiliar because I have been defining the density in momentum space all along. Because after all, there was this all. If you remember, how was those B's defined? The bosons, they were defined in terms of the density of right movers in the momentum space. So I haven't spent too much time explaining how to define density in real space. Of course, you might think that it's just a Fourier transform, and you would be more or less correct. But there are some subtleties here because of the uh, the infinitely many states issue. So remember that right at the beginning, I told you that you have to be careful about multiplying two things at the same point. So that would be true if energy states that are occupied. But you can do something else, which is you can either do this or you can do the other thing that you say that, well, my density continues to be this. This is a density fluctuation, okay? The density of right movers minus the density, average density in the Virasoro primary state. Now, this would be sensible only if uh, you ensure that the number, I mean the momentum, that's technically all the way from minus infinity to kf. That's when all the states are occupied. So instead of saying that it goes all the way from all the occupied goes states go from minus infinity to kf, you just say, well, it goes up from minus k max to kf. So, and then later at the very end of the calculation, you set k max to infinity. Okay. So if you're willing to do that, you don't have to struggle with this limit and all that. You can continue to define this, it will be finite. Okay. So if you want to set k max to infinity, you have to use this very funny definition of this called point splitting. You have to use this. But if you're willing to do this, then you don't have to use this funny point splitting. You can continue to do the familiar thing. And then finally you send Kmax to infinity. So that's what I'm going to prefer. So I'm going to prefer this method because it's easier for me. So remember that in the momentum space, this is how we define density. So the question is, we want to link the real space density, which is defined in this way, to the momentum space density, which is defined in this way. So to do that, you just insert the Fourier decomposition of the fields into this definition of the density fluctuation, and you will see that it splits up into two terms, one which doesn't depend on position and the other which does depend on position. So the thing is that so uh, first I'm going to show that the term that doesn't depend on position is finite. That's very critical, if a term that if an operator that doesn't depend on position or any operator in your formalism, it has to be finite in some sense, that If there are some, if it acts on a certain state and the result is infinity, then it's not acceptable. So remember, that's the reason why we have been uh, so careful in making sure that all our operators are normal ordered. So we have taken extreme care to make things normal ordered because we don't want to see infinities in our calculations. So here too, we have to ensure that this term that appears to be independent of position is not infinity when it acts on some peculiar state. So the way to show that is to um, okay. So firstly you show that this is finite. So now this is going to be finite because it's see it's a sum over all the k's from minus kmax to kf and it's bounded. So remember that if kmax was already infinity, this would not be finite. So that's the reason why I put a kmax there to make it finite. So this part, so this part is finite. So this part is finite. So that makes sense. So that I'm showing that both sides are finite. So the left hand side makes sense only if I subtract something which is finite from by I have to subtract a finite quantity from an operator. I cannot subtract an infinite quantity from an operator. That makes no sense. So I have to first ensure that this is finite. So that's going to be finite. Remember that I have not used any point splitting. So the way this is the reason why it's finite because there is a minus k max there. Okay, so that makes it finite. And so the question is, how do you ensure that this operator is finite? Okay, so this is going to be finite if we postulate that all states of the Hilbert space of a practical problem have the property that they are fully occupied for sufficiently negative case. So if that's fully occupied, then remember that this is 1 when k is occupied. And then this is also going to be 1 because see the idea is that those states are not never going to get depleted even when there are interactions in the problem. So the interactions are going to only scatter electrons which are close to kf to the excited states. They're never going to deplete the deeply filled states, deep into the negative infinity region. So that means when k is large and negative, those states are safe from scattering, that they will always be fully occupied and no scattering mechanism can ever dislodge an electron so deep into the occupied region into an unoccupied state. So as a result, this will always be 1 even though it's an operator, so it won't fluctuate. It will always be 1 if k is large and negative. And this is anyway already 1 because that k negative is occupied. So as a result, this whole thing is 0. So in other words, so if k is sufficiently negative, it's going to be 0. So as a result, this makes sense that it's not going to, if k is sufficiently positive anyway, this is 0 because this is 0 minus 0 because k is, I mean, if you go to regions where things are unoccupied, this anyway is 0. So the whole idea is that the number of k's for which this is non-zero has to be finite. So that's achieved by ensuring that the states for very large negative case are always occupied and there's no way you can deplete them, in which case these are not 0 but they're equal. They're 1 minus 1. So if k is large and positive, it's 0 minus 0. If k is large and negative, it's 1 minus 1. So in both cases these are 0 and you are safe. So as a result, you get x dependent independent term. So you have this rho x is in terms of oscillatory quantities and a term which is independent of x, but crucially that term is finite. See, if it's not finite, you can't use this. Okay, so the idea is that now you go ahead and rewrite this in terms of So rho is in terms of the bosons. Okay. So that's the whole idea. So now I go ahead and insert this into the so one other thing is that you see, since I have not specified what these exterdependent independent terms are, um, it's important that we consider a situation where they're not important. I mean, they drop out of your final analysis. So that's going to be the case if I postulate my interactions as such that even the W has the same property, that if I integrate over all x, I get 0. So this is going to be the case, for example, if you know, well, you have to select your V in such a way. Okay, so this is going to be the case in if you select your V such that well, see, if you suppose this admits a Fourier transform, you can write this as minus iq e raised to minus iq x minus x prime summed over q times vq. So all you have to do is ensure that the q equal to 0 Fourier component of v of x minus x prime is 0. So that will automatically ensure this identity. So in the Fourier decomposition of this function vanishes when the conjugate momentum is 0. Okay, so if you ensure this, then these constant x independent terms drop out, and then you can write your interaction between the right movers in terms purely in terms of the bosons. And because of that, you see the terms which are just b into b will drop out uh, because of both q and q dash are positive, and the b into b will force one of them to be positive, one of them to be negative. So that is why that's going to violate this constraint that both have to be positive. So such terms don't exist. So the only terms which will survive for rho r into rho r are these two terms, beta gar b and b beta gar. So, and further we say that VQ, so V of Q, which is the Fourier component of V of x minus x prime, not only is that 0 when Q is 0, it's also 0 when Q is large compared to some cutoff. So in which case that this summation is constant. That if I can pass this across, remember that these are bosons. So if I pass this across, I get 1 plus b dagger b, but that one will add up with this, and then it might give me an infinite answer unless this v becomes 0 for large enough q, so which is what I have assumed here. So in that case I get these two results for interaction between two right movers, interaction between two left movers. Similarly, I can write down the interaction between left and right movers, and that's going to involve you know, not b dagger b, but br times bl and b dagger l times b dagger r. Okay, so this is where all the non-trivial physics comes from. Because after all, here, all this does is it kind of modifies the Fermi velocity by vq. So the what was vf will now become vf plus vq by 2 pi. So it's not going to do anything dramatic, but this is going to be doing something dramatic because it involves two annihilation of bosons. But rather than there was one boson creation, one boson annihilation. So anyway, so putting them all together, you get so the total Hamiltonian with interaction is the kinetic energy of right movers, left movers, uh, RR interaction between right and right, left and left, and right and left. Okay, and they're all normal ordered in a proper way. So if you do all that, you get this result. So this is going to be your Hamiltonian. So now the question is, how do you diagonalize this? Okay. So the way to diagonalize this is there are many ways of doing it. The one way is I postulate that this is the diagonal form that, see, remember there are two species where there R and L. So after diagonalization, there should again be two species because the number of species should be faithfully represented in the diagonal form. So I'm going to assume remember these are, as far as the bosons are concerned, they're constants. So they just carry over like this. They were there here and they still are here after diagonalization. So now only the B's have been replaced by the D because now the B's were off diagonal when you have right left in. Now after diagonalization you have only the diagonal form in the D's. So now the D's are so this this is the way I do it. I write the D's as a linear combination of the B's. So on the one hand it will be like this. So you can show that these are just these are just numbers. These are not operators. These commutators are just numbers. So you can verify that this makes sense by take the commutator of dq1 with b dagger qr. What do you get? So what do you get if I take the commutator of dq1 with b dagger qr? What do I get? So what do I get when I take the commutator of d with the b dagger qr? So what is the commutator of b dagger minus ql and b dagger qr? So what is the commutator?
It will be 0.
Oh, this will be 0, but this one?
Uh, which one?
Okay. So if I take dq1 commutator, so if I try to evaluate this object by taking commutator of dq1 with b dagger qr, what will this whole thing become? It will become, you just said, it will become what? Remember that these commutators are numbers, they are not operators, they are coefficients, they're just numbers. So what is the commutator of this with b dagger qr?
1. This one.
No, dagger minus qr, b dagger qr.
Sorry. Hello.
What is commutator
Yeah.
of B dagger? Look, you understand the question of you are staring at this answers right now. I have written D as a linear combination of these two operators, BQR and B dagger minus QL. So the coefficients are just numbers, but I have still written them as commutators. But there is a reason for that. The reason is that uh, I could have called them alpha, beta, or something, but I didn't want to do that. I wrote them as commutators because if you take this and take the commutator with B dagger QR, what do you get?
Computer. Okay.
So these things are hello, hello.
Oh, I'm listening.
Yeah. So I don't know, but I think this is some sort of projection you wrote. Like when you operating the B dagger, like the B dagger QR, you will get the same thing you're writing with the commutator.
Yeah, exactly. So that's the whole idea. So if I take this and take a B dagger QR, this is going to drop out because B dagger L will commute with anything which is involving R. So this whole thing becomes zero, and this will be an identity. So it will be a DQ1 commutator B dagger QR, and this B dagger commutator is 1. So you'll get this equals the same thing. You got that? You get DQ commutator B dagger QR equals DQ commutator B dagger QR, right? I mean, you will get
Yes, yes.
identities. Yeah, so that's the reason why I've written it like this. You in all the books you will see they will struggle. They'll first give it unnecessary names like alpha, beta, gamma, delta. Then they will struggle. I want to just minimize the number of steps. So I have already called this the commutator. So it's easy that way. So then what I do is I take this form of the Hamiltonian, and then I take the commutator of say dq1 with this. So then I'll get omega q1, which is the eigenvalue, and so then I take dq1 commutator the Bosonized form of the original form of H, which involves the B's. But then remember that the only commutators which survive with respect to the Q1s are the with B dagger Q and B minus QL. So I only retain those commutators and I get this result. Similarly with DQ2, it involves B dagger minus Q and BQR. So if I do this, I get this result. So now I just have to proceed further and again take the commutator of this with the various b's, and then I will get some eigenvalue equation for omega q2, which I think you should do that yourself. Okay, and then we will be able to find the diagonalized form of the Hamiltonian with interactions, and then I'll tell you what to do with it. I mean, it will teach you certain things about. So that's quite remarkable, isn't it? That you have a theory of interacting fermions, and you are able to diagonalize it exactly. Uh, at least this is how it is for chiral fermions. So that you have chiral fermions interacting with each other. This right, left, right, everything, right, left, and still the whole thing can be exactly diagonalized. So, but then there is an issue in the sense that